Hey everybody, we are back to a late night edition of the 2024 STEMNetX Data Science Workshop. It's me, Mike McCracken again. We're up to lesson 3.1. Again, we're in the part of the workshop where we're really talking about applications that we can put together with the very simple Python syntax and kind of Python know-how, programming know-how that we've assembled in just a few lessons. Today we're going to talk about a technique, the power of which is very difficult to overstate. So fitting models to data or fitting curves to data. Data is one of the ways that we really use data to generate knowledge. And this is one of the ways that experimental science and theoretical science interact with one another. We'll talk more about that in just a minute. So in the motivation section here, I've given you some examples. This is like almost a greatest hits list of examples of curves fit to data. They range from the late 1920s and the discovery that we live in an expanding universe, which is pretty wild, evidence for the Big Bang, all the way up to predictions made in the early days of COVID when the number of COVID cases would go to zero and we could all get on with our lives. So I mentioned COVID in the data visualization lesson. This is an example of data analysis gone horribly, horribly wrong. I would encourage you to check out all these examples. Might be hard to connect on a human level with the idea of the Big Bang, but connecting with predictions about how COVID would look when we were really in the heat of it is fairly easy to connect with. I will let you read this fitting and model optimization as an idea section on your own. I'm assuming that most of the people that are participating in this workshop have used a program like Microsoft Excel or Logger Pro to fit a line to data. And it's a pretty standard thing to do. Sometimes we do it even when we don't have a good model that we want to use to understand the data that we're working with. Sorry, some wind just kicked up in my house. Let's just go straight to an example. So in this example, what we're going to do is I have prepared a data file called springstretch.csv. Here it is there. Here it is being opened in a block of code that we're going to run in a moment. And what this data file contains is a bunch of fake, I made it up, data about the force exerted by a spring and given different amounts of stretch of that spring. So if you've taken an intro physics class or if you've ever held a spring in your hands and played with it, you maybe know that as you stretch a spring more, it becomes harder and harder to stretch. It exerts a larger force. Most springs in some nice regime of their stretching obey what's called Hooke's law, which just means that the amount of force is proportional to the amount of stretch. And here is a mathematical equation that tells us Hooke's law. So the force that's exerted in the x direction is equal to k, which is just some constant for a spring. It's called the spring constant, times x, and x is the amount of stretch. I'm having a hard time pronouncing stretch tonight. So x is just a distance. It's the amount of stretch away from the spring's relaxed length. This proportionality is a magical relationship. This linear proportionality is exactly the type of model that we want to work with in the physical sciences. We don't always get to. There are wicked nonlinear systems that we actually wind up working with. But this is kind of the place that we usually start in our exploration of the physical universe. So what does this proportionality mean? Well, if I double the amount of stretch, then the spring force will double. If I quadruple the amount of stretch, then the spring force will quadruple. As you stretch a spring, it gets harder and harder to stretch. So let's plot this data. Let's just read it in. This block of code, this code cell, has a bunch of stuff that we've seen before. We're importing some libraries. We're opening the file in read mode. We're initializing some empty lists. We read a couple lines off of the file. We continue reading lines. We're splitting them into arrays. Our lists, we're appending the values in those lists to our two empty lists. We close the file, and then we plot this thing. So let's take a look at this data. There it is. Look at our beautifully formatted matplotlib plot. Now, as I mentioned a moment ago, this is contrived data. I made this data up to prove a point and to work well with the lesson here. On the horizontal axis, we can see the amount of stretch in centimeters. That's the x value in that equation that we looked at above. And on the vertical axis, we have the spring force. It's measured in newtons. If you've dealt with newtons before, great. If not, also great. And we see that as the amount of stretch increases, the amount of spring force also increases. So that's lovely. This is looking like a very nice linear relationship. It's really only this wonky data point right here that's making us maybe question this. Now, a very unsophisticated approach to working with this data would be to throw away this data point. We're going to talk about a much more sophisticated and correct way to deal with that data point later on. So we're going to leave this in here. Don't think of it as an outlier. It's just part of our data set. Now, what we want to do is we want to come in and fit a line to this data. If we fit a line to this data, we are basically encoding this Hooke's law relationship. If we can extract the slope of that line, that slope should match the spring constant. And usually when we try to characterize a spring, that's the thing that we want to know. The spring constant tells us how tough or wimpy the spring is, how many newtons of force we will get for a certain amount of stretch or many different amounts of stretch. All right, so we're going to fit a line to this thing. Now, normally if you were using Microsoft Excel, there's like a fitting panel, a curve fitting window. You got to click all over the place. You got to highlight the data that you want to fit. Oof, oh, there's a lot of mouse usage that you have to do there. In Python, or in probably many other analysis programming languages, this is the way we proceed. So the first thing that we're going to do is we're going to define a function. That's something that we learned how to do in day one, at least module one of our workshop. So I'm defining a function. I'm calling it linear function here. It's going to have 3 arguments. The function has 3 arguments, and this is strange, right? So one of the arguments is the independent variable, x. If we're thinking about our graph data above, this is the amount of stretch. It's the x ordinate of each of the data points. Then we have 2 more arguments that go into this function, but these are things that we typically don't think of as arguments to a linear function. They are m, the slope, and b, the y-intercept. So the function, its functional form is mx plus b, m times x plus b. It's just a linear function. Notice that we are returning that whole thing, and in this case, we are treating m and b as unknowns. In what happens below, m and b, we don't know these things a priori. We don't know them just from looking at the graph or whatever. In fact, m, the slope, is the thing that we want to learn by fitting this line to our data. The fitting procedure treats those as what we call fit parameters. What the fitting procedure is going to do is it's going to wiggle around m and b until it finds the values of m and b that best make our line fit our data. So that's the whole name of the game. What the fitting algorithm is going to do, you can see it in the next code cell down there. What it's going to do is it's going to start plugging our data points into this function and wiggling around, not really, wiggling is an untechnical term here, wiggling around the values of m and b until it finds the optimal values of m and b that make the function best fit our data. All right, so let's actually execute this code cell so that this is a real defined function. All right, now what we're going to do, here's all the code we need to do this fit. It's 2 lines of code, right? After we define our function, we read in our data and everything. We're first going to import a new library. This library is part of SciPy, Scientific Python, and it's the optimized package in SciPy. We're going to import this thing called curveFit. CurveFit is a function that fits a curve to some data. In this case, our curve is actually not curvy, it's a line. Curve is just kind of a general term here for a function. Here's how we call it. So curveFit is the function we're using. I have to supply some arguments. The arguments go in this order. The first thing that I supply is the name of the function we are trying to fit to our data. The second thing that I supply is the list of the independent variable coordinates in our data set. So this x's thing is a list that I created up here when I read in the data. There's x's and there's f's, those are the forces. That's the next thing that I feed into curveFit. The last thing that I have to provide for curveFit is this thing that is given the name P0. You'll notice that it's a list, it's a 2-element list of values. What P0 is its initial values for those 2 fit parameters. So our function has 2 fit parameters, a slope and a y-intercept. I need to give curveFit some idea of, ballpark, what should those values be. Otherwise, curveFit is going to start its optimization process probably with 2 randomly generated values for these things, and they might be so far away from the actual optimal values that curveFit will have a hard time reaching those optimal values. Now, I should mention that this isn't really a huge problem when we're fitting something simple like a line. In a very small amount of time, we're going to be fitting some very complicated functions where supplying these initial parameter values is very important. So again, we're calling curveFit, we're supplying the name of our function, a list of x values, a list of y, or in this case force values, and then a 2-element list of initial values for those fit parameters. I'm just going to run this code cell, and okay, so it took a little bit of time. It ended, and we don't get any output here. Now, what did happen is that you'll notice I called this function, and then I took whatever the output of this function is and set it equal to these two things, or stored that information in these two variables. The first thing that we're going to look at is this spring popped variable. So I'm just going to print that thing out. Okay, check this out. It's a 2-element list. The first element, what this list is it's the final optimized values of those two fit parameters. So up here, here's the initial values we guessed at. We just ballparked it. You know, I looked at the data when I was writing this lesson, and I was like, it's like, I don't know, 3.4, something like that. Here are the final optimized fit parameters. And I should be able to, like if I just change these things slightly, so if I start this at 3.0 and rerun that cell so that I'm redoing the fit, I wind up with basically the same values of the optimal fit parameters. So we would say, if we wanted to sound really fancy, we would say that this fit is very robust to the initial values of the fit parameters. I can change them. I don't really have to get them very close in order for this fit to reach a good final state. Like if I set the initial slope guess to be equal to 1 and then run the fit, let's see what I wind up with. Same thing. I mean, that's pretty good. So I don't have to be very careful with those initial fit parameters. I will change this back just to 3.4 just so I don't drive myself nuts later on. And then rerun this. Okay, so at that point, we're basically done. We've taken data, we created a model, we fit that data, we defined a function to represent our model. We fit that function to the data, and here we have the optimal values of the parameters in that fit. So if I wanted to use this model, this thing, 3.16989, would be the optimal value of the slope of this line, and we would interpret that as the spring constant for our fit. How do we actually know that this is a reasonable fit? Well, we'd actually probably want to plot it. There are some ways to do it with kind of summary statistics, things that are a little bit beyond the scope of this course. For our purposes, we're just going to plot this thing. We're going to take these two optimal values of the slope and the y-intercept, and we're going to feed them into our model, and then we're going to plot that thing on top of the data. So here's how we do that. I'm first going to create a whole bunch of x values. So this is a little piece of NumPy. This is a little NumPy function. Linspace creates a linear spaced set of values between the minimum, which I'm setting to be 0, the maximum, which I'm setting to be 10, and it creates 101 points evenly spaced between 0 and 10. When I run that thing, I get a list X range that has 101 values in it. I'm then going to apply that linear function that we defined. I'm going to apply it to those x values that I made with this linspace function. So I'm creating a list of x values. Sorry, I'll go this way. A list of x values. I'm applying my function to that list of x values and getting a list of force values. And I'm just going to graph those things on top of the same plot with the data points. So here, this line, you'll recognize that this stuff is just plotting code. This line plots the data. This line plots the model with the appropriate model parameters. And you'll notice that when I applied the linear function to this x range, I supplied spring popped the 0th element of that thing and spring popped the first element as the slope and y-intercept values. Those are the optimal fit parameter values. All right, enough jabbering on about this. Let's just run it. So check that out. That looks pretty good. This is a very good fit to this data. It's as good as you're going to get given this data. It's the optimal fit with this line. And, you know, I don't quite know what to say about this other than, you know, to an old geezer like me, this is a very nice looking graph. The fit looks good. I feel very confident about this. There's really only one problem, and it's more of a physics problem. So I told you up above that this was the theoretical application of Hooke's law to this spring stretching problem. So we have the dependent variable is equal to some slope, some constant k, times the independent variable. There's no constant term added to this. Whereas when I coded up a linear function here, I did have a constant term in that guy. So what we're going to do, the challenge for us, this warm-up problem says, you may have noticed that linear function isn't a perfect match for the Hooke's law model. The function contains a constant term while Hooke's law does not. The function implies that there would be a non-zero spring force at zero stretch distance, which is physically probably not accurate unless this is some kind of really weird spring. We're going to redo this fit with a function that better matches Hooke's law. All right, so here's the warm-up problem. The first thing that I'm going to do is I'm going to define a new function which I'll call Hooke's law func. Now, for this, I need an argument that is one of the independent variable that I'm going to apply the function to, and then I need just a slope parameter. I don't need a y-intercept. This function is going to return. What do I want? Just k times x. So the Hooke's law function is actually a lot simpler than the linear function that we used above. Okay, so there's my function defined. I'm just going to define that function. I'll get a new code cell right below this guy. Okay, function is defined. Now I want to redo the fit. What am I going to do? I'm going to steal the work that I did before. So I don't need to re-import scipy.optimize. I'm going to steal this line of code. I'm going to come down here. I'm going to paste it. I'm going to call this HL popped and HL pcov. We haven't talked about what pcov is. We'll get to that later on in this lesson. I'm going to get rid of linear function in here because the function I want to work with now is HL func. I'm still going to have the same list of independent variable values and dependent variable values. My list of fit parameter initial values is going to be a list with one element in it because I only have one fit parameter here, only the slope. Let's see, maybe I'll add all the plotting code to this thing as well, just so we can do it all in one fell swoop. Now, this is going to be all of the fitting capability right here. If I call this and it runs, it's going to do the fit. It's going to find the optimal value of k. But I'm just going to include all of this stuff so that we can get a nice looking graph along with this. Maybe we'll make it look slightly different too. All right, so I don't have to redefine x range. That already lives in memory. I'm going to rename this thing F Hooke's law model. Actually, I'll just call it Hooke's law model. We're going to get that by applying HL func to our x range. We have to supply HL popped, the optimal value of the slope there, and then that's it. And you know what? Let's do this. So I'm going to plot the data. I'm going to leave the plot with the mx plus b function, fit function. I'm going to call it linear fit function, and I'm going to add to this graph the fit that I just did above. So I'm going to call, instead of F model, I'll make this HL model. That's the list of force values that I get when I apply the optimized HL func model. And I'll call this HL. And I'll get rid of function in these labels just so it's not eating up so much of the screen there. All right, looks good. I don't want this to be red, so I'm going to change this to magenta. And I think I can make this a dashed line if I do that. Let's try it. I'm just kind of guessing here. So that's just formatting stuff. So this cell is going to do a whole lot of stuff. The first line is going to run the fit. The next line is going to apply the fit to our X range list and then just kind of generate what we will plot as a line, as this optimized line. It'll generate the dependent variables for that line, and then the rest of the stuff is plotting code. Okay, look at that. I'm going to change this to green. Let's change that from magenta to green just because red and magenta are pretty similar. So there we go. You'll notice a very, very slight difference between these two fit functions. The big difference is that the Hooke's law function has no offset at x equals 0 at 0 stretch, because there should be no force at 0 stretch. But, you know, it's a small difference, but it is more physically accurate if we're talking about a Hooke's law model. So that's the basics. That's like our test drive of this fitting code. I want to show you an example in a minute. So this linear fitting is something that you can do pretty straightforwardly with a Microsoft Excel or with a Logger Pro or many other kind of point and click analysis suites. In a moment, I'm going to show you something that you absolutely can't do in a simple point and click way. So it should convince you that this is a pretty powerful piece of machinery. But the basics are all there. I mean, if you are tasked with doing a fit in the lab someday, you read in the data, you import curve fit from scipy.optimize, and then you just kind of reinterpret this code or reapply this code to the data that you have. Notice how general this is. I'm not picking a function from a list of approved functions that my software can fit. I could define literally any function I can come up with here. You know, I could make this thing super, super crazy, and still curve fit will do its best to optimize the parameters in that function to match the data, which is pretty wild. Okay, so let's go to an example. We're going to look at some one-dimensional data. So I mentioned in the lesson on data visualizations, talked about a histogram, talked about a kind of example case where you would have a histogram. Let's assume that we're at some very large gathering and we've measured the heights of all of the people at this gathering. And those heights are stored in this file, heights.txt. So I've already downloaded this file and uploaded it to my Jupyter Notebooks browser here. So it's already ready to go. What I'm going to do is I'm going to open this thing, I'm going to read in the data, and then we'll just make a simple histogram of that data. 110 bins in a range from 110 to 220. So what this data is, again, it's fake data that I created, but it's supposed to represent the heights of a whole bunch of people at a big gathering. Heights in centimeters. All right, let's run this thing. Oof, that's what it looks like. Maybe I'll print out one other thing here. Let's just do this. Let's do this. Print len, the length of h. What's this? H array, something like this. Okay, just to see how many data are in this file. So this file contains the heights of 19,561 people. So it's a big gathering. It's a soccer match. It's a football match, you know, something like that. It's a big get-together. All right, so what do we see here? There's some statistical fluctuations in the data, but to me, it looks like we have basically a Gaussian or a normal distribution peaked around, I don't know, 170 something centimeters, and then we have some kind of funky bump going on down here in the tail. We want to try to understand this data set better. One thing we could do as a kind of a first pass is we could just calculate the average heights of all of the people in this data set, and we would get a value that's, I don't know, 170 centimeters, something like that. But that probably wouldn't be a good characterization of what's actually going on in the data set, because this distribution does not look symmetric. It doesn't look like we have a whole bunch of people whose heights are evenly distributed about an average height, because we have this bump going on down here at lower heights. So what we are going to do is we are going to fit a function to this data. We're going to fit a couple functions to this data, a simplish one and a more complicated one. Now, it might seem like that's a weird task because we didn't read in two-dimensional data. All we did was read in a bunch of heights. So how are we going to fit to just one dimension's worth of data? What we're going to do is we're going to turn this histogram into basically bivariate data. We're going to turn it into a series of heights that are basically the centers of the bins in this histogram. And then the vertical axis information is just going to be the heights of each of one of those bins. So you could maybe picture, instead of a histogram, just kind of a scatter plot graph where the tops of each one of these bins in the histogram is just a data point. It has, you know, it's at a certain height, and has a certain number of people represented at that height. The way that we do this, so you may, if you're really paying close attention, you may have noticed that I set the outcome of plot.hist. I stored whatever the output is in this bin values variable. Let's take a look at that now. So if I go down here, we'll find out that bin values, let me print bin values itself, bin values is actually a very big, it's a list of lists or an array of arrays. The output, this output is a list containing two lists. So here is bin values. It starts here. It's this first array, goes from this square bracket up to this square bracket. You'll notice that the values in this first array are just a bunch of integers, and it looks like they're the heights of the bars in our graph. So what's the tallest of these guys? What's the largest number? 739. If I scroll back up to my histogram, that looks like this bin right here. It's 739-ish events tall. The second of these things, yeah, here's the second list right here. Here's the second list right here. It looks like evenly spaced integer values of centimeters. So these are the edges of the bins. This is the left edge of the first bin, the right edge of the first bin, and then it's right edge of the second bin, right edge of the third bin, right edge of the fourth bin. I can grab each of these arrays individually. If I grab the 0th element of bin values, I get just the first list. It's this thing here. If I grab the index 1 element of bin values, it's this thing here, and you can just see those are the same lists that were represented up above when they were packaged together. I also printed out here the lengths of these two guys. So bin values 0th element and bin values first element have different lengths. There are 110 elements in the occupancies list, the heights list, and there are 111 elements in the edges list. The reason for that is that the edges list contains the left edge of the first bin all the way up to the right edge of the last bin. So it actually has one more datum in it than the other list. What we need to do is we first need to take this edges list, the list that contains the bin edges, and turn it into a list of bin centers. The way that we do that, it's a very kind of dumb averaging process. I will let you read this on your own. There's nothing sophisticated going on here. We just loop over that list and create a new list called bin centers. That's just the average of the two successive bin edges. I'm just going to run that cell and forget about it. Here I printed out the first 10 elements in my bin centers list. You can see instead of 110, 111, 112, I get 110.5, 111.5, 112.5. And there are now 110 elements in that bin centers list. Okay, so I should be able to plot these two guys together. That's what it looks like. So just like I mentioned a moment before, we want to think about converting this histogram into a bivariate distribution, where on the horizontal axis we have the bin centers, and on the vertical axis we have the bin occupancies. Now we can think about fitting this thing. I'm going to go through this fitting code very, very quickly because I don't want to show you the syntax. I showed you that above. Instead, I want to show you the power of this tool. So the first thing that we're going to do, this kind of looks normally distributed. Let's fit a Gaussian to it. All right, here's what a Gaussian function looks like in LaTeX and fancy math speak. I have some magnitude, some height, a, times e to the power minus the height value. This is going to be the independent variable that we read in, minus mu, which stands for the mean, the average of this distribution, squared, divided by 2 times sigma squared. Sigma is what we call the standard deviation. You can think about it as the width of that Gaussian distribution. So if we increase mu, this whole distribution would slide to the right. If we increase sigma, that whole distribution would become wider. So sigma tells us about the width of that distribution. If we increase a, this whole distribution would get taller. What we want to do is we want to fit this nasty Gaussian function. Is it linear? Heck no, it's not linear. We want to fit it to this data. Now that would be a very, very complicated thing for a point-and-click analysis tool to do, but we can do it with basically the same code that we had from before. So again, I'll just show you the code and run it, and we'll see what kind of fit we get. First thing we're going to do is we're going to define a fit function. I'm calling this fit function single Gaussian. It takes in 4 arguments. I have the independent variable h. I have then my fit parameters. So the a fit parameter, the mu fit parameter, and the sigma fit parameter. I named them the same dang symbols that I have in the actual expression above. Then I'm going to make this fit function just return exactly that function. So I have a times numpy exponential function. So np.exp just means e to the power whatever is in parentheses, minus h minus mu, minus h minus mu squared divided by 2 divided by sigma squared. Complicated function, pretty easy to define using Python. I'm then going to run curveFit. I'm going to call curveFit. I'm going to store the output of curveFit in this Gauss popped and Gauss pcove things. I have to supply the name of my function. I have to supply the bin centers, the independent variable, the variable that's on the horizontal axis, a list of those things. I have to supply a list of the dependent variables, the bin occupancies. And I have to supply a list that's initial values, guesses for the initial values for the fit parameters. I'm guessing that this distribution is about 500 tall. You know, that's fine for a ballpark. Its mean is at about 170, so 170 centimeters is about right there. That looks okay. And the standard deviation, the width of this thing is about 20. I've been looking at Gaussians for many years now, so I can kind of just see that that's the width. You don't really need to know that off the top of your head. So we're going to fit this thing, and then we'll print out the optimal fit parameter values, and there they are. The fit went very quickly. The height is 662. The mean, the average of that distribution or function, is 173 centimeters. Standard deviation is 11 centimeters. We can also test this to see how robust this thing is to those initial fit parameters. If I change the guess for the mean to 100, which is pretty far off, we still wind up with, basically the same values. I'm going to change this back just so I don't think I'm losing it later on. Just like we did before, we want to graph our fit function along with the data. I'm going to do that in the same way. Yeah, do the same thing down here. So use a function. Okay, so same type of thing here. So function values, I'm going to apply this to the bin centers list, and then I'll graph all this stuff. Let's do that now. Hey, look at that. So here's our distribution, same histogram that we saw above, and here is our optimal fit function, our function using the optimal fit parameters shown in red. The fit is, it's pretty good. It seems to be capturing this large bump very well, but it's basically totally ignoring this stuff that's happening down here. The reason for that is it can't not ignore that stuff down there. This Gaussian doesn't have the ability to make this double bump shape. All it can do is one bump. The fact that this data down here, this little shoulder that we have to the left at low heights, is not represented in this shape means that this fit really isn't as good as it should be, because that data over at small height values is going to be pulling our fit function over that way to try and make the fit function represent that data a little bit. What we really want to do is come up with a more nuanced model that we think might describe this data. So I'm going to do that now. What I'm going to do is I'm going to make a fit function that isn't a single Gaussian, it's actually 2 Gaussians added together. So we're going to say, hey, there's some balloons for you all. We're going to say, hey, what if this data is actually 2 populations? So maybe it's some adults who are characterized by a mean height of 170 centimeters, and also a smaller number of kids that are characterized by a mean height of, 145 centimeters, something like that. How do we do that? We do it using the same dang technique that we used before. I define a new function. I'm calling this double Gauss. I have 2 different Gaussians, G1 and G2. They have the same functional form that we had above, but they each have their own height, mean, and width parameter. So this function is going to have 1 independent variable and 6 fit parameters that the fit will wiggle around until it gives a good fit to the data. I fit this double Gaussian function to the data in the same way. So I supply the function name, the bin centers list, the bin occupancies list, and now I have to supply a list of 6 initial fit parameter values, fit parameter initial values, and then I call curve fit. I'm going to print out the optimal fit parameter values, and I'm also going to do the graphing. So this cell right here basically does everything. It does the function definition, the fitting, and the graphing all in one fell swoop. Let's take a look at it. I should mention too that this code cell is going to plot, just like with the Hooke's law, the spring stretching, this cell is going to plot our previous model, which wasn't a great fit, and this new double Gaussian model, if it works. Let's see. If it works, look at that. All right, so again, here we are seeing our histogram. I've shaded it in this time just so we can see it a little bit better underneath these functions. The red dashed line is our old fit function, single Gaussian. The green dashed line is our new fit function. This is very, very difficult to do, right? There's a lot going on here. We have 6 fit parameters, and Python was able to plow through it quite easily. At this point, we can extract some knowledge from here. So it seems like this data is described well by a double Gaussian fit function. The larger Gaussian has these fit parameters. So it has a height of 674, a mean height of 173. So that when I said height before, I meant how tall the function is, not the people. That's a little bit confusing. And a standard deviation of 10.56 centimeters. Then the smaller Gaussian has these parameters. It has a magnitude, let's call it, of 86.99, a mean of 141.5, and a standard deviation of 7.78. Pretty powerful stuff. At this point, you could start to make some guesses about what this population is. Maybe it's a big concert that mostly appeals to grown-ups, but there is a small number of kids at this concert, or a smaller number of kids that were dragged along to this concert. Something like that. So there's a lot going on there. Now at this point, I'll let you read this gut check stuff. Why would we learn these skills? It turns out these skills are incredibly powerful for doing careful science. I'll let you read through these at your leisure. I think they're very eloquently stated, but your opinion may differ. Put a comment down below. That'll be helpful. The last thing that this lesson goes into is extracting the uncertainties on these fit parameters. So again, we've taken some data. We're now fitting a function to that data. When we fit that function, Python, or curve fit, is giving us what it thinks is the optimal value of each of the fit parameters. There is uncertainty in our measurements. Therefore, there will be uncertainty in any results that come from those measurements. Any type of scientific result you have will have an uncertainty attached to it. Fit parameters are no different. So if I have a spring and I stretch it and I measure the stretch and the force, there's going to be uncertainty in those things, and the fit parameters, the slope, the spring constant that I measure from that data will also have an associated uncertainty. So how do we get that uncertainty? This is very technical. It has to do with that second thing that was being output when we call curve fit. So the first thing is just a list of the optimal fit parameter values. The second thing is a mathematical entity called the covariance matrix. It's very sophisticated. If you've dealt with linear algebra before, that's great. If you've done statistics and dealt with covariance matrices before, that's fantastic. For our present circumstances, all you have to know is that second thing that's output is a matrix of values. The squares of the uncertainties of each fit parameter are the elements on the diagonal of that covariance matrix. So if I want to get the uncertainty on the first fit parameter, that is the square, or the square root of the 1, element of the covariance matrix. That's all the more I'm going to say about how to do that. If you want to see how it's actually extracted from the fit, you can go through this last section of this module. So here, to extract the fit parameters, or the uncertainties, I'm printing out the covariance matrix, and then later on, we can actually parse these things out. So if I execute this cell, we see that for fit parameter 0, the optimal value is 674, and the uncertainty on that quantity is plus or minus 4.5. so you can see how to actually extract those things. If you want to dig more into it, that's great. But when we do a fit, the fit parameters will have uncertainties associated with them. This is how we extract them. Lastly, and I'll let you comb through this section on your own, I mentioned in a previous lesson on data visualization that our experimental measurements will have associated uncertainties. Matplotlib allows us to plot those uncertainties in an error plot. Those uncertainties also affect our fits. So if we go back up to, let me just plot it right here. If we go back to the spring stretching data, here's the entirety of the spring stretching data set. Here I'm also plotting the error bars that are included in that data file. So we talked a little bit before about how this point here at 7 centimeters looked really wonky. It didn't seem to fall in line with the rest of the data. That looks very linear. And that is reflected in the data set by the fact that this data point has much larger uncertainty on it in the vertical direction. So maybe it was measured with a different device. Maybe there's some reason that there's more uncertainty or less precision associated with this data point. What that means for our fit is that since we are less certain about this data point, it should affect our fit less. When the fit is actually run, when curve fit runs, it should try less hard to actually reach this point than it does all of these other points that have smaller uncertainties. And curve fit is sophisticated enough to figure that out. So I'll just show you the syntax for doing that now. I'm just going to craft a new or define a new function, linear func error, that contains, it's an mx plus b linear function. And I'm going to fit this thing to our data. The call of curve fit looks very similar. I have the name of my function. I have the independent variable list. I have the dependent variable list. But now I'm also specifying the vertical error bars, or the uncertainty on each one of those data points in the vertical direction along the vertical axis. And then I have some initial fit parameter values there. So I fit this thing, and I'll show you a plot. So this graph shows the data points, obviously. And then the fit function, when we don't consider the errors, is shown in magenta. You'll notice that it's a little bit lower because it's trying to scooch down and get closer to that wonky data point. The green fit function is the one that we get when we do consider the error bars, and it's higher because it knows that this data point down here is less certain, and it shouldn't try as hard to try and reach that thing. So this is a very sophisticated process. The actual math of trying to do this fit with error bars or with point-by-point uncertainties is quite complicated. You don't need to know about that. You just need to know that it is a thing that you can and should do with Python and with curve fit. So there you go. We have a nice little summary section here. Then we have some homework problems. These homework problems they're going to look pretty challenging, but they are actually just rehashing the skills that we've used above. So kinematics data with errors, this is going to be fitting of that, a fit of that to that parabola data, t and y error. So this is a data file that we looked at before. How would you do this fit? Same process as above. You would basically copy all of the code from this last section of the notebook and just define a new function and read it in the data a little bit differently, and there you go. The NBA data, again, this is a data set that we've seen before in previous homework problems. Here, fitting a histogram with a Gaussian, great. The temperature data is an interesting one. So the idea of this problem, this is one that I've given for like a decade, it's actually a really useful problem, is you're going to use this function and fitting to some temperature measurements in Washington, Pennsylvania to extract the length of a year. Now, you know how long a year is. It's 365 and a quarter days, and there's like some weird fractional seconds, after that. But you can also look at, observationally, if we look at the temperature in Washington, PA, can we extract the length of a year? If you've worked with oscillatory functions before, like in a physics class doing simple harmonic motion, this might come a little bit more naturally to you. If you've not done that before, maybe skip this problem. It is interesting though. This problem relies very heavily on choosing good initial fit parameter values. So there's your hint. There it is, fitting to data. Very, very powerful tool. Look forward to you taking it for a test drive. I'll see you in the next lesson. Thanks.